Okay, when do I start then? In 1 minute? A warm welcome to all of you for this session on distributed embedded intelligence for a sustainable industrial society. On the practical side of things, I would like to mention that there's a possibility for you to ask questions. They will be handled by the speakers towards the end of the presentation. In case we should not have time to handle all questions, I'm sure they will later on take contact with you for answer your further questions. But let's go immediately into the real presentation. I will pass the word in a minute to Peter Hellinckx. Peter Hellinckx is professor at the Idealab, an IMEC research institute at the University of Antwerp. Peter is also heading the AI team. And also for this presentation, he brought quite some colleagues with him to join the presentation, but he will introduce them further during the presentation. So enjoy the session, and Peter, it's up to you for your presentation.
Thank you, Sabine, for the nice introduction. So hi, I'm Peter Hellinckx, head of AI at Idealab in Antwerp. And today what we want to do is to present what we think about embedded intelligence for a sustainable industrial society and how we see it implemented in real industry. But let's start with the beginning. First of all, what is Idealab about? Let me switch slides. Idealab is a research team from IMEC, and we are located at 2 universities, in Ghent and in Antwerp. And in Antwerp, we're really focusing on 2 things, on connectivity and IoT, the 5G things and everything around that. And on the other side, distributed artificial intelligence, what we are going to talk about today. In total, we are like 350 researchers, but in Antwerp, we are almost or a bit more than 100 people, guided by 7 professors, 4 business developers, more than 10 postdocs, and then 80 plus researchers and so on. Who are those people? On the top, you see our valorization team, and we are a bit of an atypical team in a sense that we really focus on valorization. You could look at us as a bit as a company where we could, or where we at least try to focus on solving problems from industry and for industry. And based on that, we are doing that research in the 2 domains, in the wireless networking and in the distributed intelligence. And here you see the different professors that are focusing on that. On the left, you see Jeroen really focusing on wireless networking. And all the way on the right, you see Steven Lattre, who is working on distributed deep learning. And then you see the people in the middle that are going from really wireless to really core distributed intelligence. But what do we want to talk about today? Really about 2 things, or at least we believe that the introduction of everything around networking, IoT, and cyber physical systems on the one hand, in combination with the deep learning, the machine learning, and everything around artificial intelligence, will make a big difference in the near future, for not just for you, but for companies in all different application domains. And the future we believe in, I always show this movie. It's a bit of an old movie, and it's a fake, of course. But anyway, it shows at least how we see the world in the future, or how we think that we should try to go towards a fully optimized, controlled world, in the sense that based on these technologies, we can make sure that the different processes in our society can work optimally. And how do we want to achieve that? And that is really important. That is more or less the structure that we are working with. Is we want to start, of course, as a research team from fundamental research, and that's what you see at the bottom. And we have 2 strong teams in that fundamental research. One team really focusing on how do we place AI in a constrained environment where resources are not fully available, where time is an issue, and so on. And the other side, really a fundamental AI team focusing on different types of algorithms, new algorithms, looking at causality, looking at explainability, and so on, but backed with an AI application team, a team that really makes that translation of these constrained technologies and those fundamental AI technologies towards an application domain. How can we fit that in industry? And of course, then we are still not in the industry, because you see industry is really on top, and there is like a whole range of domain-specific knowledge needed to put those technologies that we have really in the application domain. And how we approach that is by trying, or at least what we are really good at, is in combining that domain-specific knowledge with that application expertise. And the way we tackle it is by trying to combine the R&D teams in industry with our applied research teams to get finally into a deployment in industry. What we really are proud of is that if we do something, we want to be to make sure that it is valid for industry. And when we zoom a bit more into depth, then we see that we have those three teams at the bottom, the sustainable AI systems team, really focusing on the resources, distribution of resources, even really go to specific techniques like neuro-inspired techniques. On the right side, the advanced AI techniques, explanatory AI, causal learning, relational learning. And then on top, the AI application domain, where we do two main things. First of all, control, really focusing on how can we control different things, ranging from chemical plants towards autonomous ships, HVAC systems, and so on. And on the other side, because we also have the expertise in wireless networking and how to intelligently control our network and our spectrum and the things on that. And we do that in different applications domains, like the smart ports, the processes, chemical industry, smart construction, wireless networking, and so on. Question we often get is, there is something called the AI Flanders project, where they are also doing a lot of things. How do you relate to that nice initiative that is running right now? And it's pretty easy to explain. I think when we look at the AI Flanders program, there are 4 research challenges. One is on AI-driven data science, one on AI in the edge, then one on multi-agent collaborative AI, and then on one on human-like AI. When you look at our teams and the 2 bottom teams, the more fundamental teams, then you will see that we really focus on 2 of those domains. AI in the edge, everything about the resources, where we're doing a lot of, really energy consumption related things. And then we have the lead in the human-like AI challenge as well, where we incorporate our other things. What will today look like? We will further zoom into the different aspects. On top, you will see Christian, who will really focus on how we bring things into the application domain, how we work together with industry. Then on the bottom left, Werner will talk about resource constraints and how we tackle AI problems within a constrained environment. Tom will talk about those advanced AI algorithms that are created within our team. And then Siegfried will talk about how to combine these techniques into real applications in control and wireless networking. But first of all, let me give you the word to Tom, who is the manager of the advanced AI team.
Okay, thank you for the introduction, Peter. So let me immediately start with what's probably the best example of advanced AI today, and that is cat or a dog. Are you detecting a cat or a dog in this picture? And here we see, luckily, that our AI system is capable of detecting that there is a cat in that picture. And that's probably one of the most used examples of AI today. But is that really what we need? Is that really what we want? Why? Because this is actually the perfect example of what you could consider internet AI. Why? Well, you have a lot of data. You use a lot of data examples to train your algorithm, to train your model to do something. For instance, to detect a cat or a dog. But you also need a lot of computational power for that. It's typically something that's running in a data center somewhere at the other end of the world, where there is a lot of resources available to be able to run your algorithm and to be able to detect something. And more importantly, a lot of that data is provided by people, by us, both by taking pictures in this case, but also to manually annotate those pictures to be able to give that information to the algorithm, to the model, to do something useful with that. And that's actually a bit the current state of the art in AI. We're very good at detecting certain things, certain patterns. But from a more philosophical point of view, from a fundamental point of view, is that really something that we would call intelligent? Here I took a quote on intelligence from a very well-known site. And if you look at the things that they sum up, for instance, capability of logical, reasoning, planning, creativity, all of those things, is that something that we would link to the previous example I just gave? And for me, the answer is at least already no, that's not the case. Why? Because if you look at existing AI techniques and the example I just gave you, they all are very specific. They all work on one specific task. For instance, detecting a cat or a dog. They're a black box. You have a model. The model is capable of detecting certain things, but you and I don't know how the model does that. We don't know why a certain results come out of that. And in particular, as I already mentioned, there are a lot of strong constraints. We need a large pool of data in order to be able to train a model to do something useful with it. And we have the strong affiliation with resources that are needed to be able to run your model. And all of that, if that's not already enough, they all are very expert systems. They need domain knowledge. They need experts to be able to handle those, to set up those models, etc. I think we should need to go to other types of AI appliances. In general, we should envision a future AI, and I'm speaking on a long-term scale, where you can make a model that's capable of working in different types of contexts. Yes, you have the generalization principle, and it's able to adapt to new tasks, to new settings very fast. I think that's a very strong difference if you look at the current state of the art. Those models need to be able to understand really what's going on in their environment. It's not simply detecting what's going on or detecting a certain object in a picture, but also being able to reason, like a human a bit, on what's going on in that scene. How is that object related to other things that are happening at the same time, for instance? And preferable, the systems are explainable. They're capable of explaining their decisions in some way or another. I will discuss that later on. And also, they need to be interactive. If we now interact with AI systems, this is currently not really in a natural way, like we talk to a friend or to a colleague. It's more like, pressing a button or typing a certain command or something like that. That's not really the way we would like to go. And also, if you look at this slide, there's something very important that I didn't mention yet. And if you look at the existing AI techniques, they're mostly pushed by large multinational companies that have all of that needed resources available. They have large pools of data. They have the money to invest in those products. They have the computational resources to be able to run and train those algorithms. And that's not something that you will typically see in our neighborhood company here in Flanders. They have typically less data available. They don't have that much resources. And I think that's another motivation next to, in parallel with the more fundamental vision on it, that we need to change the way we're using AI models and how we train them, etc. So that's another motivation for that future AI perspective. So let me zoom in a couple of solutions, techniques that we're working at Idealab Antwerp. And there are three, and Peter already introduced them to you. So I'm going to talk about relational learning, causal learning, and explanatory AI. Let me start with relational learning. If you think about what an AI system currently does, it can detect something, but it can't link that object that it detects, for instance, that cat, to other things that are happening in the scene. And one of the techniques there we're pursuing is actually graph neural networks, because a graph can structure data in an intuitive and easy way. And we're trying to use those techniques to reason about a certain scene environment. For instance, you see the small example at the bottom where you have some balls laying around, some objects laying around. We could ask questions then to that algorithm. Yeah, okay, is there a certain object next to another object? So you get that relationship between objects in your algorithms, and that's something, yeah, completely different towards the state of the art. So we're looking into those reasoning, taking into account those relations between objects. Another thing we're looking at is hierarchical reinforcement learning. Why? Well, reinforcement learning is something where you, in contrast to state of the art, where you use large pools of data as examples for your algorithm, reinforcement learning will typically learn by example, by interacting with a certain environment. And there we're seeing that current state of the art is not good enough, and we want to introduce a bit more like human-like learning reasoning. Why? Because if I would step up out of this chair and walk to the fridge to get me a drink, then I don't think about all the intermediate steps that I need to take to get there. I just get up and I go to the fridge. But for instance, a robot would need to think about all the individual moves that he needs to make to get there. And there we want to make a separation between higher level abstractions, so to say. Go to a certain room, go to a certain object. That's something that you can reason about on a higher level than the small, low level steps you also need. And that's something we're doing at Hierarchical RL. And now, a third thing we're looking at is exploration, because typically, especially in unseen environments, there will also always be an exploration step because you need to adapt to that environment. Let me zoom in on one specific example of our research there, and it's related to the hierarchical reinforcement learning that I introduced. Here we're actually trying to use language as a tool to learn faster. For instance, imagine you have a robot and it knows already that there is, for instance, a fridge in the kitchen. And then you ask that robot to go to the oven. And by using language, we can go faster in that learning process, because you already see that the slide there as well. The green line is actually the way to the kitchen, so to say, and the blue line is then to find the object in that room. And by using language, we can go much faster. That's something you see here at the graph. Disregard all of the lines, but just look at the purple circle. You see that there is a massive increase between the blue and the green line, certain for that algorithm that has that input of language. That's one very concrete example of our research we're doing in that front. Doing research is always nice, but you also need to couple it to a real-life use case. And that's something that we call Embolic AI, where you can really instruct an AI system or a robot, for instance, to execute certain tasks or answer certain questions. For instance, in this case, you ask, in the example, the robot, okay, what's the color of the car? But it doesn't see a car. And then it needs to look around and think in an intelligent way, okay, where could that car be? How do I get there? And then answer the question. And to go to really go beyond state of the art in that domain, we coupled it to our own offices, actually. I see that the screen sharing has stopped in the meantime. That's a bit annoying. Let me try to come back to that. Okay. There we are again, hopefully. So we actually made of our offices a completely digital twin. And where there in that simulated environment, we can train our robots to do certain tasks, and then we map them to the real world. Here you see a dummy example, but we can do actually much more with that. So for instance, here you really see a robot that is being trained in a photorealistic environment to be able to execute certain tasks and move to certain rooms, etc. So I think it's something that's, we are also pursuing leads, for instance, in logistics, to couple that case to an industry setting. Going further, another type of technique, another type of research we're looking at is actually causal learning. And I have to thank the media and what's going on currently with the COVID vaccines on that, because they gave me the perfect example there. Because currently, you probably all know that, but a lot of countries are suspending the use of AstraZeneca vaccinations. Why? Because there might be a causal dependency with certain things that went wrong. So some people got some blood problems there, and the countries or the agencies are investigating if there is a causal relationship between vaccination and the event that happened afterwards. And so currently there is no proof of that causal relationship. There is only a correlation. That's actually also something that we're looking into. We're trying to make AI techniques that are capable of detecting those or making those causal relationships. And more importantly, in contrast to what's previously already been done, we're not only capable of doing that in known data, but we're really trying to discover new causal dependencies that we didn't know of before. And we're trying to do that in real world situations. And I'll give an example of that on the next slide. And one type of data that's very interesting to look at in this case is topological data. So let me zoom in on one example. This is some research we're quite proud of, actually. And here we're trying to detect those causal dependencies, causal relationships in time series data. Because we're exploiting the fact that even if something happens in a time series and you look at a variable later on in that series, you know that has happened after the initial event. And we can try to exploit that using deep learning techniques and build a causal graph out of that. You might say, okay, great, you can do that, but what's in it for me? Well, two things actually. One, we're currently already exploiting those techniques in the context of a European project, Future Arctic, where we actually try to investigate the impact of global warming on certain ecosystems. Okay, great. It's still far from your bit probably, but the same techniques can be, for instance, applied to production plants where you try to interconnect certain events that are happening or trying to investigate certain problems that might arise. How did that problem arise in the first place, and how are things interconnected to that event? A last type of research area we're looking into is explanatory AI, because we already talked about it previously. An AI system currently can't explain their decisions, and often it's quite black box type of model because we don't know what's going on there. So explanatory AI is really an important research domain as well. And actually, we need to first distinguish two different things there. That's model interpretability and explainability, because before you're going to explain what a model is doing and how a certain classification or a certain result came to be, we need to also know actually what that model is doing and how is that model learning. And that's the difference between interpretability and explainability in there. And that's an important fashion. And what you see here on the picture is actually we first do an interpretation step where we try to see, okay, what's a model using to make a certain classification, and then we try to explain it also in a visual fashion, so not explaining it in language, but using a visual tool to heat map actually to highlight the certain reasons of the regions in an image on how they're influencing the final result. This links closely to representations, because the moment you know how a model interprets certain things, you also want to make new data representations that includes more information that a model can utilize in the process of learning, for instance. So representation is a really important aspect, and it also couples back to a previous point that I brought up, that are those graph relationships, representations where we try to incorporate those relations between objects, for instance. One case where we can apply that research and that explainability and interpretability aspects is actually towards security and towards detecting if something goes wrong. So in the first case, there were already examples around the world where they could trick a certain AI algorithm into predicting something completely wrong. And also recently, once more, there's some buzz about detecting fake images, and actually the human that you see on the screen is a fake image. But by using those explainability techniques and those interpretability techniques, we can highlight actually why that is a fake image. So the images at the right of the right screen where you have that heat map overlay on it, they're actually highlighting things that indicate, there's something wrong with that image. So So there are important aspects in the world of AI of today, of course. And then lastly, using that same interpretability, you can try to distinguish different features and break them down into small components. What does that mean? Actually, if we want to, for instance, keep the shape of a certain object, but we translate the style of that. And here you see an example of that, where we want to go from images from just random peoples, and we want to bring one aspect out of that image, in this case clothing, and then you want to map it to catalog images. And that's you're seeing at the left side. And at the right side, you can go one step further, and you really create a virtual clothing trial on, where you map those certain features, certain aspects of an image that you have. You can separate that from the other things in that image, and you can reuse that image in different styles, in different translations later on. I think that's my final slide here. I want to summarize it with, we're basically going beyond what currently AI systems can do, and we're really wanting to go towards more intelligent approaches. It can also be adopted by industry players here in Flanders. And with that, I would like to conclude my presentation and to give it over to my colleague Werner, who is going to say something about sustainable AI systems and how we can apply those new algorithms that we're developing also in a resource-constrained setting.
Thank you, Tom, for the introduction. So I will talk about sustainable AI systems. What we do in this research area is mainly coupling the AI algorithms and models that exist and that we have, which give you certain accuracy or prediction accuracy or classification accuracy with real systems to be deployed in the world. When you're going to use these AI algorithms, basically you have to take into account on what type of processor, what type of computer I want to put it on, and there will be constraints coming with that practical aspect of it. It can be about power that you have available, about latencies that you can get, about other software running on the same system, and so forth. So we combine the AI algorithms with system aspects to come to a final solution to be deployed. So in fact, our view of in the future, we will see AI in all and everyday objects around us. You see distributed AI systems in Industry 4.0, where basically the intelligent algorithms will run on the robots, they will run on sensors, they will run on machines, and they will run on computers. It will be a collaboration of many, many different intelligent entities, all on their specific systems with their specific constraints that you have to take into account. Also in mobility solutions like self-driving cars, you will see that in a car actually will have multiple AI systems doing multiple things. They will be constrained with the environment where they're running in and with the power and the compute and memory power that is available. For drones, it will be even worse. Drones will not always have all the connectivities. Power and weight is a very stringent requirement there. And so you want to fit the algorithms at the correct processor, at the correct accuracy in those constrained devices. And if you go even further to wearables, very tiny devices, very low power, and still you can use very advanced AI algorithms there to do interesting things for healthcare, safety, and in society in general. So these are all the applications that we want to target, and the focus that we have in this research area is looking how we will build the system so we can run the AI algorithms. Sustainable AI systems are, of course, important. You can it is in 3 dimensions that it has to be sustainable. On the one hand, low power, obviously. If you want to run AI everywhere, you cannot spend kilowatts or megawatts of power all the time in big server farms. It has to go down to watts, milliwatts, or even below that if you want to have fully distributed AI systems. Devices have to be small and have to be easy to use. So if you need an AI processor or an AI accelerator that you want to introduce in your product, you want it to be small and you want to be able to easily integrate it into your product. I need something AI. Okay, we will come with a big truck with an AI system. That's not going to work. And finally, it has to be accessible and affordable, because the cost of a system is a real thing that you need to take into account building systems. So also for the AI part, if you want to augment your system with AI capabilities, you want it to be cheap, and you want it to be so that you can actually integrate it in your system at an affordable cost and people will buy your products. So today I will highlight two tracks that we are actively researching. One of them is ResourceAware AI, and the second one is a little bit further into the future. It's beyond second generation neural networks, which I hope will come clearer later on. ResourceAware AI. So what we are trying to do in ResourceAware AI, basically, we take the big neural networks. So the big successes of AI today are mainly all about deep neural networks, a huge amount of neurons, many layers, many connections, and they achieve very high accuracies on a variety of tasks. Now, if you're going to go to a resource constrained system where you don't have all the memory and all the processing power available, one technique that we are investigating and that we are making different variants of is network compression. So basically what you want to see is, can I compress my neural network to a smaller version which still has acceptable accuracy? So you might actually, in reality, you might compress your network drastically with one order of magnitude or more. You might compress it while only losing a fraction of the accuracy of the classification. Depending on the task that you want to do, depending on the application, you can actually compress your network. You can also play with the weights. You can have the granularity of the weights, how accurate have to be my calculations to come to an acceptable solution. Again, by playing on that dimension, you might gain a lot on be able to build simpler systems that still have acceptable performance. So that's one research line that we have in this ResourceAware AI sub area. A second one is that more and more systems are having multiple sensors available to sense the environment. And on each sensor, basically, you can do AI algorithms to recognize objects or to do interesting things. So you can have a drone that has cameras, but also has radar and has other sensors on it. And of course, you can build systems that use all that information, all those signals, put it in networks and get the best possible perception of the environment that you're flying in. But in some cases, that's not necessary. In some cases, you might just work with only the camera or only the radar, and it will be good enough. So there might be certain tracks when you're doing certain jobs with your device that you don't need all your sensors. So you might actually switch off part of the neural networks that you don't use. You might save power in that way and so forth. If you come into a complex situation, you switch everything on, you go to peak power, and you use all the information that you have. A third track that we are doing is data quality. Data quality is very important for AI systems because in the lab or in benchmarks, you get perfect data or you get very nice clean data, and you work with that, you make algorithms. In reality, you have noise, you have missing data, reporting works, reporting sometimes doesn't work, and you have to take care of that. Now, you can take care of that with more advanced neural networks. You built in redundancy, you make more complex algorithms, but you don't always need that. So data quality is about looking at the data quality that you actually get and then decide what type of network you need in that sort of environment or for that application. And again, taking into account the architecture and the resource constraints that you have from the underlying platform. And finally, we work on network architecture search. That goes on finding the optimal architecture to do a certain task, and not only the optimal architecture based on performance, on accuracy, or for prediction or classification, but the optimal architecture based on the hardware architecture that you have available. So if you have certain hardware constraints, you have a task where you want to reach a certain type of accuracy, what would be the best network architecture to do? So the network architecture itself becomes the object of the investigation on how the architecture should be before you start learning the architecture and doing the thing you wanted to do. Another track, of course, which is very important, is resource consumption analysis. What we do is based on the software that you have or the AI algorithm that you have and that you want to run, and the specification of the hardware, you want to do some sort of prediction. What is the worst case of resources that I'm going to use in this? And then the question is, can I run this or can I not run this? So in fact, what we're doing here is we're using AI models to look at AI models that will run on the hardware and sort of make predictions. What can you do, what you cannot do, and in what cases you will need all the resource or can you work with part of the resources? This can work both for software and existing hardware that you will use and where you have the characteristics from, but can also be used in hardware, software code design cycles where you use these tools to decide, well, if I have a certain task and I have certain requirements, how should my hardware look like if I can afford to define or design new hardware to do these things? You can use the same type of tools. And the last track that I want to highlight in this area is inference distribution. So when you have this distributed system or you have this factory deployment where you have AI systems in all types of different devices or capabilities to run those on different compute platforms, where is the best place to run your AI things? So you have to do that based on latencies that you take into account, but available processing, available power, and so forth. So there are algorithms to, once you know what you want to do and what algorithms you want to run, which part of the algorithm you're going to run on what device. And of course, it is a combination of processing the AI, via AI, the signals, and communicating between those devices. And the communication is also very important because it depends on, is it very secure? Is it always available or not? Or you want to do things autonomously or not? So for all this, we do a multi-objective optimization algorithm based on heuristics or reinforcement learning or variance to decide for a particular problem in a particular situation, where would be best to run the algorithms that you need to solve the problem. So this mainly is all about taking today's deep neural networks, which is the huge success story of AI at the moment, and trying to fit them on real-life devices, taking into account constraints of the devices in power, memory size, processing speed, and so forth. Now, besides this, we also look at the next step in the future and what will come. So one thing that will come is beyond second generation neural networks. So today's are all second generation neural networks in that case, of course. And they were inspired by the brain, small computational elements called neurons connected via synapses, which have a weight, and you sort of construct your function to do object recognition or classification based on training the network. And training the network is adapting the weights of all the connections, so it makes a function that does the thing that you want to do. Now, if you look at the brain, and the neuroscience is continuously evolving. In fact, in the brain, signals are not represented by scalar numbers that you have to multiply. And multiply a signal with the weight and then add it, and that's how neural networks work today. In the brain, in fact, the information is represented by spikes. There are just small spikes of electric activity that go over the axons and the synapses. And based on that, those spikes, they get integrated on some sort of membrane potential. And when the membrane reaches a certain value, the potential reaches a certain value, another spike is sent down the line. So that's the basic mechanism that exists. And there are many, many different ways of doing that. But there is a fundamental way of representing information as spikes. So by looking at that, the third generation of neural networks will actually build also hardware that will use spikes to transfer the information and not using the scalar numbers. Because what we have seen today is that if you want to really go to ultra low power neural networks for deployment, you can use second generation neural networks, but you probably need deep neural networks accelerators. And what they basically do is they try to accelerate and reduce the power of the multiply and add cycle. So multiplication of signal values with weights, adding them all together through a nonlinearity, and to calculate the result is basically taking all the processing requirements and all the processing power that you need. Now with spikes, that will be completely different, because with spikes, what you have to do is you basically have to integrate spikes on some sort of a membrane and just count when the spikes reach a certain value, and then you generate a new spike. That's the basic element. And there is some leak. The membrane has some leak that if spikes come in, after a while, it will leak away. And only if enough spikes come in a certain time interval, there will be a new spike generated. Now, if you look at that from an electrical point of view, in fact, the most simple model for a neuron, you can model electrically as an RC circuit. An RC circuit with some sort of mechanism to trigger a new spike when the voltage over the capacitor reaches a certain value. So it's the spikes is the current coming in. There's a small current coming in. The charge goes on the capacitor, and there is a resistor that models the leak from the capacitor. And then when the capacitor voltage reaches a certain voltage, you generate a new spike and you reset the whole thing. So that's the basic electric circuit that you would need to model one neuron. So besides the fact that it models better this spike-based communication and the spike-based computation, it also opens the way for totally new hardware design. So besides complete digital design, in fact, here you could do an analog design. You could actually implement this stuff with RC circuits. So the basics that we want to take in these third generation neural networks is, first of all, brains, they use spikes to encode information and not real values. And then the question, of course, becomes on a computational level, how do you represent signals in an optimal way with spikes? And there are many different ways of doing it. So one of them is rate-based coding. Basically, if the signal is stronger, you send more spikes per time unit. So the rate of the spikes sort of indicates how strong the signal is. Another way of doing it is more temporal codes, where you say, no, it's when the spike is sent that will present the information. If it is a high value, I will send the spike sooner. If it's a low value, I will send spike later. So in fact, you only need one spike or a few spikes to represent the value if you can play with when you send the spikes, and if your system can handle that when the spikes are coming is important to understand what it represents exactly. So there is a whole point that when we're going to work with spikes, how do you represent input information and how do you compute with that sort of spike trains to compute new things? On top of this, then you have to build learning systems, of course. So you have to build learning systems using those spike-based computing elements. And one track is it's a complete imitation of what we do for second generation neural networks. You basically find a way to do training via backpropagation or backpropagation through time for time-based networks. So it's really what we have understood from second generation neural networks. We're going to apply to third generation neural networks. We're going to train them exactly the same way. In practice, it means when we run these on simulators, we also get the same results. So we get the same results with the same training rules and with the same types of networks. We have convolutional neural networks today, and we have spiking convolutional neural networks for the future. In that case, in fact, the only advantage we might have is that the hardware might need less power to execute. So the whole point of doing that track is that if we can build hardware that is much more efficient on spike-based than on a deep learning second generation network with an accelerator, we gain on the power. Now, another potential advantage, which might be more important or more interesting, is that brains also use local learning rules. Local learning rules means that you don't need backpropagation, or the fact the brain does not do completely backpropagation. Whenever a sample is given, you look at the error and then you update the whole network weights to just get better to it. It uses local information in the vicinity of a neuron to update the weights and to update the behavior of a neuron. Now, this way of working has advantages that you can build unsupervised neural networks in another way, and you can also find ways of adapting a neural network while it is running, while it is being deployed, if you have this mechanism in place. So we're looking at these local learning rules and see what we can do with those to find new types of learning algorithms, and as a result also put them in potentially novel applications that need this type of learning. And finally, what we noted, of course, is that brain activation, in fact, is sparse. Right? So we have many neurons, but not all of them are active all the time. So it's not that whenever it's an input that all the neurons in the network have to be updated and recalculated. There are mechanisms that certain neurons will fire and they will inhibit other ones that will not fire. And that's also a way why you achieve significant amount of lower power uses than having to run all the elements all the time. So that is the basics where we're looking at. What we can do with that. So as I already said, there are two main, I think, application areas. On the left-hand side is what we have today and what I like to call static intelligence. And so you train your neural network in the cloud with many data samples, many cases, you get optimal accuracies, and then you're going to try to deploy it in a device. And then, of course, you can do all those things that I said before. You can do a model compression, you can try to squeeze it in, you can find ways of having other architectures that fit better. But at the end, you will put your model in the device, and there it will do execute only. That's what deep neural networks do today. They execute, and they always do the same thing. So given a certain signal, they will do the same thing. If they get the same signal tomorrow, they will do the same thing. Unless you go back to the cloud, you retrain the network for some other reason, and you download a new network. That's, of course, then you get another behavior, but normally it always does the same. And there is this whole industry, and it is a big success, and you get many interesting applications for that. However, moving on, if you want to go to more dynamic intelligence, if you can manage to do learning on the device, or adapting on the device, you might do different things. So you still have a pre-trained model, because why would we not do a pre-trained model? If we can do that, we just put a pre-trained model there. At least it has some knowledge about the situation it has to work in, but then you let the device actually learn new things. Now that can be adapting maybe to some environmental conditions. Maybe the lighting is different, the weather is different, you want to adapt a little bit. It can also be other context elements. It can be personalization. You have a certain algorithm that is doing a certain recognition, but it depends on some factors of the human using it, and you might actually adapt it on that. If that is a personalized device, you might adapt the algorithm based on the behavior of that person and get better results. So these are the two things that we basically want to do. We want to run them very efficiently in the hardware, and we want to explore what sort of local learning we can do and what sort of new applications we can build with that. So 3 types of applications that we are doing at the moment as examples. So one of them is we're doing, so we did some applications on hand gesture recognition based on a radar. We actually did this with a spiking neural network, and we found that we actually outperformed the 2nd generation neural networks state-of-the-art results on that. So the idea is really that the user can do any of 10 or 11 gestures, and the system has to recognize which hand gesture the user did. Very interesting here is what we also found out is if this, in this case, it was a radar-based system. If the radar is on a handheld device or on a device that is personalized to you, we found out that it gives much better results if you train the system per user than if you train a system based on 100 users and try to deploy the same system all the devices. So the general system gets to 95–96% accuracy, but if you train the system or retrain the system for a user, so you let the user that will use the device train the system with 20 more gestures for each, 20 times each gesture again, you get to 97–98% accuracy. So actually the local learning for personalizing the thing improves the accuracy as well at the end. We have other projects on urban sound recognition that we have deployed in the city of Antwerp, where the idea is that we want to monitor certain sounds and do a reporting based on the type of sound and the severity of whatever it is. It can be used for emergency situations, for police type of things like gunshots, explosions, alarms going off, that there is a signal sent that there is something going on in a certain area. The very specifics of the legal system in Belgium is, of course, you cannot record sounds and send them to a central system because you cannot record voice. That's not allowed. So what we have to do is we have to run the AI algorithms on the sensor itself, on the box. So what we do is we do the sound recognition on the sound device, and we send the classification result already to a central system. Here also we need adaptation because we are investigating that. Do we do it with one single system? Each sound device has the same algorithm to detect the sounds, or do we adapt? Because depending where those devices are being installed, you get different acoustics, you get different street. One of them is in a park, one is next to a bar, and you have to sort of filter out the background. So it has to adapt slightly to the environment to get optimal results. And finally, we are interested and we're working on wearables, where wristbands or chest bands or other types of things, they measure biosignals, and there are algorithms that allow us to predict things like stress or anxiety based on the signals that we can get. But again, it's very, very personal. You can detect from a human when he's stressed or not based on signals that you get from a wearable, but the base signal is very different from one human to another. Just take heart rate variability. We have all different basic heart rates, so it depends on the person what you have to start from. So also there, we think there is a lot of advantage to be gained, that we can adapt the system and we can learn actually for the specific human person using that system. So this is a few of the examples that we are working on, applications that we are working on, and the technologies. And with this, I will pass the word to Siegfried, who is managing the AI applications and will tell you many more interesting applications of our work. Thank you.
Thank you, Bernard. Okay, let me share my slides. Okay, so as Peter and Bernard already said, I will give you a brief introduction on what Idealab does in terms of AI-driven applications. Now, within the AI applications cluster, we actually focus on 2 primary domains. So on the one hand, the intelligent control systems, focusing specifically on system controls, for example, autonomous shipping and process control, for example, in chemistry and in HVAC, as well as, of course, network intelligence, where we use AI technology to optimize wireless communication resources. Now let's dive into control systems first. So in a typical control setup, whether it's an autonomous vessel or a chemical plant, you have your system equipped with sensors and actuators, which is designed, of course, to perform a specific task with a specific goal in mind, and of course, subject to disturbances from the environment. Now, the controller side, regardless of the type of algorithms used, typically you have some sort of representation of the system and its environment, so a model, simulation technology, basically, and an intelligence that decides how to actuate the system based on the current and past sensor inputs. Now, in conventional controllers, the system would, for example, be governed by linear or nonlinear differential equations. In our research, however, we focus, particularly for the controller part, on machine learning technology. So you might wonder, why exactly machine learning? Well, in model predictive control, some of the main challenges for classical control approaches are actually dealing with complex nonlinear systems, usually due to the nonlinearities or unknown dynamics in the systems that can be difficult to model. In addition, we always have to work with the limited observations of the plant or the environment based on the sensors we have available. We might not be able to capture all of the possible disturbances. And of course, we're often also limited by the capability of creating that simulation model or representation of our system. Now here, machine learning can actually help us in two ways. So first of all, in terms of modeling the system and its environment, we can use data-driven machine learning-based modeling techniques to capture the complexities of plant and environment and better capture the behavior of our system that would not be possible with the classical modeling techniques. In addition, of course, we can also use AI to develop more advanced and more intelligent data-driven control and optimization strategies, and even design entirely new strategies, for example, by exploring the control space with techniques such as reinforcement learning, effectively finding novel solutions without requiring an example of, for example, an existing control system. Now, of course, machine learning is also not the silver bullet. It also has its limitations, and the gap between fundamental research and the state of practice is often quite large. So therefore, the AI applications cluster of Idealab focuses strongly on the methods to bring these fundamental AI concepts into practice in domains such as automotive, autonomous shipping, and process control for chemistry and HVAC. So for the remainder of the presentation, I will focus mostly on these different challenges in bridging that gap. So if we consider our control system again, so this could be, as I said, an autonomous ship or a chemical plant, for example. A first challenge, of course, lies in the perception of the system and perception of the environment and the system that is being controlled. Now, sensors, of course, only give us a very limited view of the system and its environment. And the decisions that our agent will make are only, of course, as good as the view it gets on the world and the input data it receives. So therefore, it's important to understand, like Werner already mentioned, to grasp the properties and the reliability, of course, of our input data. So first track really ties in closely with our research on ResourceAware AI. And a first approach is actually by analyzing data quality parameters of the input data. So by making an assessment of the quality parameters of a specific sensor, if for video, this could, for example, be the amount of blur, overexposure, or noise on the image, we can decide whether or not a sensor is suitable for our intended application. We can then also further analyze the impact of this noise on the models and see how it propagates throughout our network. And based on that, decide whether a certain set of input parameters is sufficient for the robustness that we desire of our control system. And then, of course, as explained in the talk on the ResourceAware AI, we can also start looking into context-aware selection of the optimal combinations of sensors or even optimal models for that specific context. And so not only does this provide us with insight in the reliability of the system, it can, of course, then also be used to create more intelligent switching behavior. Now, another approach is of course to look into external data sources. So typically each agent in a system, and for example, when we're talking about autonomous vehicles or autonomous ships, each agent has its own partial observation of the environment. The view of the agent at the top here, for example, is obstructed by the house, so it won't see what's happening behind here, while the agent at the bottom has a very clear view of the area in front of it. So another approach to further improve perception of control systems is to dynamically and opportunistically ingest information from nearby sources, for example, the other agents in the environment. And so in distributed perception, we can merge those individual observations into a global worldview and basically sharing that information between the agents so that they can, with that additional information, make more informed decisions or perhaps anticipate to, for example, in the case of autonomous vehicles, the things happening much further along the road. Or, yeah, like in this example, to improve safety when approaching a road. Now, where are we using this technology? For example, in the Blue Cluster Icon project on shared situational awareness for vessels, we are using a combination of both the distribution and the quality aspects. We were making quality aware decisions on which information to share across multiple vessels from either the fleet owner's own fleets or also across the fleets of different stakeholders. Another project where this technology is applied is, for example, the Horizon 2020 5G Blueprint project. So the focus on in this project is mostly on 5G technology for cross-border transport and logistics. And in terms of distributed perception, here we're looking at distributed perception solutions similar to what we're doing in the SAFE project for teleoperated vehicles. Now, of course, even with accurate perception, we don't necessarily cover the entire problem. Even with the best input data, a lot still depends on how good we actually understand the behavior of the system that we are trying to control. And this often reflects the quality, is reflected by the quality of the simulation model that is used by and even the most advanced simulation models can still be a limiting factor, as they might deviate in some way from the actual planned behavior. For example, because there are certain high-dimensional properties that we didn't model, or because there are external disturbances that we don't fully understand or can't fully predict. So here, machine learning can help us in various ways as well. So, for example, when looking at the modeling of the system that we're trying to control, classically we would, for example, work with a white box model. A white box model is usually based on deterministic equations with understandable behavior that is often modeled based on mechanical or physical laws. Now, of course, when we want to model it at a very high level of accuracy, we will end up with very complex, computationally intensive models. So an alternative approach, which could potentially be computationally more efficient, is to go for a fully black box approach. Here we derive the model of the system solely using data. So really trying to mimic what the system behaves like. And of course, although this could potentially have benefits in terms of computation, the downside is that it's no longer fully understandable. We have no clue what exactly is being modeled inside that black box. And it's also very difficult, of course, to validate then whether the behavior actually correctly approximates the system model. So a third approach, and an approach that we are using in the Catalyst Adapt2Chem project, is to use a combination of both, really trying to exploit the benefits of both approaches. So what we do is we start with a white box model, which we try to bring as close to the actual system model as possible, and then extend it with a black box component or multiple black box components to add, for example, the higher dimensional behavior that we couldn't model with the white box model, to incorporate properties that were not included in the models that are available, and so on. And this effectively allows us to close the gap between the imperfect physical system we have here and the potentially too ideal white box model that we started with. Now, the creation of these advanced models, of course, also allows us to develop and validate novel machine learning algorithms without the need for extensive testing in a real environment. And an approach that benefits from this in particular is reinforcement learning. And why is that? Well, reinforcement learning learns from interaction with an environment through trial and error. So imagine that you would have to do this with a physical setup. You would need months or years of training time for the agent to be able to capture the full complexity of the system. Whereas when using very advanced simulation, we can take a shortcut, try to approximate or let the agent learn a system that is a very good approximation of reality, and then just further fine-tune it on the physical setup. Now, how does a model-based reinforcement learning agent work? Well, basically using that trial and error process with the environment, based on the goals defined by the reward function, the agent either gets punished or rewarded for his actions. And during this learning process, the agent will build an internal representation of the environment, so as well as an optimal control policy and insight in the effects of its actions on the environment. So if you want to train it in simulation, the better the simulation environment approximates the actual system, the better the agent will behave in when we use it in practice in a physical environment. And so you can imagine that's such a very time-consuming process would be nearly impossible to achieve when using purely a real setup. So where are we using this technology? So on the one hand, in autonomous navigation, we're using model-based reinforcement learning for autonomous shipping. So in this case, we're training agents in simulation to navigate along a trajectory and avoid obstacles that they encounter along the way. On the other hand, again in the IDLAB project, we're also using model-based reinforcement learning for chemical process control. So here, what we basically do is we starting with a white box model of the flow or batch process that we aim to optimize. We add black box components to the system, obtaining effectively a more accurate hybrid simulation, which we then use to fine-tune our controller, which we can then later deploy in a testing environment to further tweak it to the actual physical setup. Now, I've been talking about controlling chemical processes, navigating ships, potentially even vehicles. And so you might, of course, be wondering, like, what exactly does the agent think? And is it actually safe what it is doing? Okay, perhaps this scenario is a bit too far-fetched, but in any case, understanding which decisions are made by the agent and how it operates is crucial, especially when we're considering critical systems such as chemical plants and controlling them. So what we can do here, and this ties in again very closely with our fundamental research on explainable AI, to better understand how the agent reasons, we can rely on explainability of AI. So for example, we can assess externally what the impact of certain input changes is on the output. We could also look into approximating our agent with a fully interpretable model, or perhaps even diving into the models themselves by visualizing the neural response or analyzing the different submodules of our model-based reinforcement learning agents. And the advantage, of course, of using that explainability is that on the one hand, it provides human interpretable insights into the system for the process operators so that they can observe what the system is actually doing and intervene if needed. So very crucial from a safety perspective. It also allows us, of course, during the design phase to analyze and verify the behavior of the agent, which is much more difficult if you consider it as purely a black box system. And of course, should things go wrong, we always have that traceability of that decision making from the agent through the information or the human interpretable information that we can extract with these explainability techniques. And this is also, of course, something that can be of incredible value when we're talking about process control in chemistry, like in the IDLAB project. Now, a final challenge, you're probably wondering how we could possibly achieve all this computationally. Well, this is where various scalability techniques come into play. So on the one hand, when we're talking about scaling up simulation, we have several tools that can help us with achieving that very large scale skill simulation that might be needed, for example, to simulate emergent behavior of very large systems like, for example, traffic simulation. One of the tools that we can use here is, for example, adaptive load balancing, where we really look into the simulation, into different actors in that environment, analyze how they interact with each other, and based on that interaction, aggregate them and also migrate them to the most suitable computational resources based on that level of interaction. And should something change, then migrate them again to more suitable resources. Another approach we can consider here is to work with different levels of abstraction in our simulation. So ranging from very accurate micro simulations to the less accurate high-level macro simulations. And by assessing the level of quality that we need in each area based on, for example, the activity or the specific applications that we're developing, we can then select for each area the optimal model based on the quality requirements of our simulation. Now, to conclude, of course, when we're talking about control, as Philip II of Macedon once said, in a completely unrelated context, we can also divide and conquer. And this is also the case when we tackle very large control systems, such as district heating systems, very large chemical installations. Now, the idea of this approach is to assign agents to various subsystems of the control system, give each of the agents only a view on part of the system, then define a local goal for each individual agent, as well as a global reward for the optimal condition of the system as a whole, and then teach the agents to collaborate to achieve that common goal. Now, crucial here is, of course, agent communication. If they only have limited perception of their environment, they should, of course, inform each other about the decisions they're making, of what they are observing locally, and try to agree on what the best collaborative strategy would be. Now, this can be done in two ways. So on the one hand, we can work with predefined communication, where we explicitly program what exactly the agent has to do. And on the other hand, learned communication, where the agents, in combination with learning an optimal control policy, also learn what messages to send to each other. And this is also one of our more fundamental research tracks, where we're really looking into the open challenges in this learned communication, such as, for example, how to define those multi-layered reward systems, how we can decentralize the training methods to more efficiently train large amounts of agents simultaneously. And of course, on how to optimize that communication, for example, by minimizing the amount of messages, passing on messages using a multi-hop system across multiple agents. Now, enough about control. So next to that research, Idealab is also researching applications in network intelligence. So what are we doing here? Well, the focus in network intelligence is on using state-of-the-art machine learning methods to optimize wireless communication systems. And this ranges from optimizing the radio spectrum usage to network bandwidth management, as well as intelligent allocation and scheduling of simultaneously the network, computational, and the storage resources. So you can already feel that this also ties in very strongly, of course, with our ResourceAware AI, specifically the applications we do at the edge and the distribution of inference. To give you a taste of our research in this area, I will briefly dive into two projects in this field. So the first one you might have heard of is the DARPA Spectrum Collaboration Challenge. So this challenge was an open competition with over 30 teams that lasted 3 years. And the goal was to design AI-driven flexible radio networks that are capable of sharing spectrum with each other without any planning, so without knowing exactly what the other agents in the environment are doing. The goal was also to learn how to adapt across multiple degrees of freedom to changes in the environment and in the conditions, and of course, to collaboratively optimize the total spectrum capacity. So what Idealab did here with Team Scatter was researching real-time spectrum usage and prediction. So basically trying to sense what the surrounding nodes in the environment are doing, then trying to predict the availability of bandwidth in the near future, and by recognizing wireless technology and trying to forecast those patterns, then create an intelligent schedule and decide when to transmit or receive information. So the Scatter team, as I said, was a collaboration between Idealab and Rutgers University, and we actually made it into the final round of this competition in the top 10, landing finally on a 6th place in the ranking with our proposed solution. So the final project I would like to cover today is the Horizon Daemon project, or Network Intelligence for Adaptive Self-Learning Mobile Networks. And in this project, the aim is actually to develop beyond 5G network technology that can deliver self-managing, high performance, and high reliable wireless network systems. And how we will do this? Well, basically here we will use AI-based forecasting, and the system actually aims to predict the computational and radio resources in the network, and in a second step, use that information to perform joint optimization of resource sharing at the edge, both for communication and compute at multiple timescales. So meaning that we're looking both at short-term and long-term dynamics of the availability of resources, again, tying in very closely with our research on ResourceAware AI. And so finally, in terms of self-management, you're also working here on a reinforcement learning agent, similar to what we are doing in the process control, to perform closed loop control of our network resources. So this brings me to the end of my part of the presentation on AI applications. So in summary, we covered intelligent control systems, where we focus on bridging the gap between fundamental and applied research, and network intelligence on the other hand, where we aim to realize the next generation wireless network technology using AI-driven technology. So I will now gladly give the floor to our Director of Valorization, Christian Leijsen, who will elaborate a bit further on how we collaborate with industry.
Thanks, Siegfried. So as Peter already mentioned in the beginning of the presentation, we at Idealab, we really position ourselves strongly towards industry. I'm going to talk a bit on how those collaborations went in the past, some examples, but also why we are doing this and how we help companies this way. So if you look at the structure of Idealab, and if you allow me to recap today a bit, this also shows our very much strong focus towards industry. For example, Tom talked a lot about the advanced AI. So what are certain algorithms and what type of algorithms that we need? Then Wegner talked about how can we apply those algorithms on certain systems or hardware. And then Siegfried talked about bridging the gap between the algorithms and the systems towards a certain domain. So there we infuse use case constraints and use case knowledge also. But then as a fourth step, the last step maybe in the chain is we also need to position ourselves towards industries. And there I'm going to highlight the 4 industries most important today to discuss. But there we also look at domain knowledge from certain industries itself. So the industrial focus of Idealab is actually on 4 domains. So we have smart port, and there we look at how can we leverage AI technology for systems in logistics, but also localization or autonomous vessels in the port environment. We have smart construction, where we focus on how can we make buildings actually smart. This in a sustainable way and also throughout its entire lifespan. So this can go from the initial design phase of a building on looking what type of sensors do we need to make these buildings more smart, but also to the end phase of a building. How can we, for example, optimally retrofit an old building to a new design? Next to smart port and smart construction, Idealab also focuses on smart processes. And this is a general term for describing actually how can we optimize industrial processes? So this can be in a pharmaceutical production company, for example, like Siegfried already mentioned a few, but also in a waste management facility, for example, where I show also some examples of in a few minutes. And then, of course, we talked a lot about artificial intelligence today, but at the core, Idealab is not only doing research at the level of AI, we also look towards wireless networking. And there, of course, there is a big overlap in the middle where we see how can we leverage our AI technology also for making these wireless networks more smart. And this, for example, is linked to the DAGBA project that Siegfried also mentioned, where we do smart spectrum usage of wireless technologies based on artificial intelligence. So these are the 4 main domains where Idealab is going towards industry. And of all of those domains, I would like to give you a small example on what we did there. And then afterwards, I will give a bit more information on how we work together with companies. So for the first pillar of smart part, we work together with CFAR on making an autonomous vessel. And you see here on the left, you see the actual AI agent learning in a simulated system to guide throughout a waterway so that it doesn't bump into the sides, that it learns to maneuver throughout the whole waterway with moving vehicles also in there. And this means that we need to create also a digital twin sometimes of these environments or simulation way. And this tightly coupled with what Tom was showing in the beginning, where you make a digital twin of our own offices. It's not that we do that only for some toy examples. We also bring this knowledge into projects like this so that we can create a very nice simulation environment of a certain domain. And we don't stop there. Because we are a very applied research group, we also bring this to a real life case. And there we work together with CFAR, for example, where we also put these systems onto real life vessels, and where we also add, for example, computer vision to give the vessel extra sensory input, so that in the future, and we have already some nice examples and of results of projects now, where we can go to a fully autonomous vessel. And in this way, we try to envision AI also in a smart part context, and this is one of the examples. Another example or another domain that we are also active in is smart construction. And this is a project that we are shaping together with the Beacon and multiple large building companies. But this is how we can use AI, for example, and also for leveraging AI in the building industry. And there we see, for example, on the left, an old building, and we of course want to retrofit it into a new and more optimized building for the future. I think in Flanders it's very much alive, this debate at this moment. And there we use AI, which can infuse lots of information, for example, multiple designs of a building, the energy consumption profile of buildings, but also pictures from the environment, for example, for suggesting the best or multiple ways of how we can retrofit an old building, so that it takes into account all that information to create an optimal new building for the future, where there is, of course, in the end, a human in the loop that can still make decisions on how exactly the building needs to look. But in this way, we can already optimize the building in a first way, which gravely can help these smart construction companies in the future as well. This is now an example of a retrofitting case, but as Siegfried also mentioned, we are also doing a lot on HVAC technology, so optimally air condition certain buildings, for example. Smart processes, I would like to give an example of Recupel, where we are working together to actually make their e-waste recognition system better. These days, it's quite a manual task, but we have together with them created actually a system where we can automatically, using computer vision, recognize the e-waste that is going through the system so that they can optimally use their facility in the future as well. We have some very nice results here, and we are working together with Recupel to see how we can take this to the next level and actually go deeper into their facility to really inline place these types of AI technologies. The last pillar I want to discuss is smart wireless networks. And here I also want to give a very tangible example where we work together with, for example, Orange, but not only big companies. We also work together with, for example, Hellinckx, which is a smaller startup company. And there we work together with them to find a solution for autonomous medical drones. So you can imagine that in the future, especially in Antwerp, it's very congested sometimes to get medical equipment or medical samples from one hospital to another. So we are exploring there the option of drones. And there, of course, we don't build drones ourselves, but we are involved there in the smart wireless network connectivity with those drones. Nowadays you have 5G, but there is also 4G, you have dedicated radio links, and you want to have some fail-safes and optimized systems in terms of wireless connectivity. So in that way, we are using also AI to optimally use these technologies and switch between them to have an always-on connection with the drone. because this is a very, very high prio case, because it's important in the medical field, of course. And there we leverage actually both our research from AI and wireless technologies. So these are a few examples on what we did in those fields, but of course we have many more examples. We work together with small startups, we work together with large companies. And I think one of the reasons why we are so successful at working with companies is that we can leverage our researchers in a very flexible way. And to make this very tangible, for example, we guide companies not only through the technical parts, but we are there from the start. Also with the scoping of certain projects, we are there, and we like to work throughout the end of the project. And once we sign the contract with a certain party, we also like to start the day after, so to say, so that we can optimally use the time and make the real innovation in the companies in a very, let's say, fast way. And this means that we work together with a lot of companies that are already on the slides, but we also work together in very close collaborations with the spearhead clusters in Flanders. And this all is supported by our very strong business development team. In terms of possibilities for collaboration with us, I'm not going to delve into the details here, but what's important is that we are very flexible in this way. We can either just go for a bilateral framework agreement between our organizations, but we also look a lot towards more the funding agencies and the subsidies together with companies to also find tracks that are applicable over there. And that's why we have that strong business development team to really guide those companies in that transition, actually, because it's not always easy to get innovation in the entire business ecosystem. So this was a very short recap of what we do and how we work together with companies. If you want to know more, don't be afraid to reach out to me. I know it's always daunting a bit, the technologies, and it seems always very, very difficult what we do. But we're actually here to help you with that. So in that sense, you can always shoot me an email, Christian Leijzen at Interpretability, so Christian.Leijzen, or on Calendly. You can also reach out to me for a quick chat to see if there's something we can do together. And in that sense, I would like to end my part on the business requirements and the business collaboration. I think I give the floor back to Peter now, or Sabine, to give the end of the presentation.
Yeah, I'm looking at the time, so I think you concluded very well, Christian. Thank you, Christian, Werner, Siegfried, and Tom for the nice presentation, and we can continue with the questions now, I think. Sabine?
Yeah, sure. Yeah. Let me also thank all the speakers because it was a very inspiring talk. Sustainability is, of course, a very relevant topic, and it was very nice to see a combination of the research topics and also for some really concrete examples that you already have shown. So I think quite some people are eager to know how they can continue with and take up this research in for their applications. So we are open for questions, so you can still add them in the chat. There's one question that I already see. The question is about security. And you already talked about safety, was mentioned by one of the speakers in the audience. But are you also worried about security? Since machine learning models are prone to adversarial attacks, and most of embedded systems are likely to be exposed to these, how are you looking into security? Peter, is that one you can take?
That's a question I can address. Azim, thank you very much for that nice question. I think it's a very good question. When I talk to my students, I always say, don't look at security the same way as you look to safety. But right now, I'm going to answer a bit differently. I think if we want to be able to address those security issues, we can approach it from a safety perspective. And what I mean by that is that if we can connect the right explainability methodologies and the right causal methodologies to really explain why certain control actions are taken or certain perception is done, then we can start tackling that. And that is, for example, I think something that Tom also mentioned in those pictures. We see all of those things happening with deep fakes. If we can start explaining why pictures are real or not real, or why certain information that is coming from somewhere that we don't know is fake or not fake, then we can start working on that part and start solving the security issues from a safety perspective.
Okay, another question. We've talked quite a bit about technical aspects, but what about aspects on ethical aspects, for instance, or aspects related to HR? So, for instance, if a company would like to take up these solutions, what would they need, for instance, regarding human capital? Are they ready to take up these solutions?
Well,
I will take that as well, probably. Of Christian, do you want to take it?
Go ahead, Peter, go ahead.
No, I think that's a good question as well. Always with emergent technologies, you need the right human capital within your company, and I think depending on the size you have and depending on where you are in the trajectory of the transformation, you will need different kind of people and different kind of teams. What I would suggest, but of course I'm biased a bit, is initially start working with teams like us to give you an initial thought on how you could optimally transfer it, and then together with, for example, us, start investing in the right people within your company. We already did that with some companies, and it works pretty fine. Companies that in the meanwhile have like 10 people working on data science because they now really feel that they need it and they have the competences in-house to support those people or to make a difference there. What is equally important, I think, in the more ethical thing, or the ethical part, is make sure if you create such a team yourself that you have different type of people involved. The more that you reduce the biases that you have in your team, the better results you will get. And also, don't look at a data scientist as one type of person. You have multiple different kind of persons, so make sure that you have people that are really good in looking at data, knowing what is good data, what is high quality, what is low quality, how do we get biases out. Then look at the stuff, the algorithms. There are other people that will really work on algorithms. What kind of algorithms do we need? And then we have the implementation phase. And never forget that you need your own people in the company with the domain-specific knowledge, because without domain-specific knowledge, people can promise you a lot, but they will get nowhere, that's for sure.
Okay, thanks, Peter. Also, a very technical question, if I may go back to a technical question. How ready are you, or how do you actually do training and inference? Do you already do both in the edge? What is already possible? And what would be the biggest obstacles to already do both in the edge? Perhaps something for Werner or Siegfried?
Yeah, I can take that. So I think today the majority is you do training in the cloud and you do deployment and only inference at the edge. And the main reason for that is that because the best known and the best working algorithm today is backpropagation, and that needs a lot of compute resources. If you have to do that on the edge, you have to foresee additional compute on the edge to be able to do backpropagation, and you need a lot of samples to train it. So the best way today is you train in the cloud and you deploy on the edge. Now, if you go into the future, you can think of we're going to do adaptation. So what I said about beyond second generation neural networks, there we have shown that we can do it at prototypes and at sample demonstrations, but not in any commercial system at the moment. So I think today it's pretty much dominant on inference only at the edge, but which has many, many interesting applications. I think gradually we will see more small adaptations on the edge, but to do the full learning, I think we will have to do some significant improvement on the algorithms and on the hardware to make that possible in a low power way.
Okay, thanks. Anybody still want to add? But I think that was a pretty good answer already. There's time for one more question. I see a very concrete one. Is Idealab by any chance also involved in natural language processing or translation technologies?
Well, this is not our focus at this moment. In NLP, we have some limited experience there as well, but it's not the focus of Idealab.
Okay. Yeah, clear. I think I don't see any more questions. And I think we're also towards the end of the session. So unless a question now pops up, I think we can close the session or wrap up the session. Let me look at the...
Thank you, Sabine.
Peter, is there something else you would like to add as a closing remark?
One more thing. I want to thank you to help us out. We were honored that you were the person that guided us through this thing. So thank you very much for that, Sabine.
Okay, thanks to all the speakers, thanks to the audience, and I hope you will get further enjoyable and interesting sessions this week and later on. And for any questions, I think the team of Peter already mentioned very clearly, they are very open and eager to hear your suggestions, your feedback, and go into further discussion and collaboration with you. Bye, see you in a later session. Voilà. Is iedereen aan het vertrekken? Of?
De meeste
Het was heel goed, denk ik.